All right, like I was saying, we are going to kind of bounce around from chapter to chapter, hit certain sections out of chapters for the rest of the text. Things that I think are going to be useful for you in the next course, maybe things that are going to be useful for you down the road in other courses that you may take before graduating high school, or something that you might get into in college. Okay. So one of these topics is simplifying radicals, which is something we talked about a little bit before we left for break. Now I know the gap between talking about it and then break, we may have forgotten. So, but we started to see some of these in the quadratic formula that we were working with the other day. So I think maybe it makes sense to go back and talk about this stuff and see if we can learn this a little bit better. And then we'll move into, once we learn what radicals are and what we're doing with them, we'll talk about some radical equations later, probably next week at some point. But the first couple days here, we'll talk about simplifying radicals. Then we'll talk about adding them and subtracting them. Then we'll talk about multiplying them and then dividing them. And when we do all those operations with them, this simplifying process is still kind of governing all of that. Okay, so it's kind of like when we add, subtract, multiply, and divide fractions. When you're done doing that, when I multiply two fractions, the last thing I do is I then simplify it, right? When I add two fractions, once I combine them, the next thing that I do is make sure it's simplified before I present my answer. So this simplifying of radicals is the last step that we will always do with radicals before we present our answer. Okay? And the reason we do this, because some people might say, "Oh, this is kind of silly. This is, why do I have to do this if, if radical 8 and 2 radical 2 are the same exact thing, why do I have to write it as 2 radical 2 instead of radical 8? Down the road, there's going to be operations, going to be math that we want that 2 radical 2. Okay, it's going to make things a little bit easier later on. There will be times where radical 8 is needed. It's just both formats are useful at some point. It's much like 2/4. 2/4 is the same as 1/2, right? Maybe in some applications, 2/4 is the route we want to go. Other applications, 1/2 is the route we want to go. So we need to be able to jump back and forth between both formats. So that's kind of what we're going to do here in the next couple days. Now, before we do this, there's some terminology that we're going to use. A radical expression is any algebraic expression that contains a square root, or could be a cube root, a fourth root, or etc., fifth root, sixth root, seventh root, that kind of stuff. A root symbol looks a lot like a division symbol, okay, except for there's a little thing out in front. So that's your root symbol. A division symbol just looks like that, right? So you got this little thing out in front. And it's really, if you think about this, what letter is that? That's an R. Does this look a lot like it? That's where it comes from. That symbol comes from the fact that a lowercase r is somewhat like that. Okay? That's the history of that symbol. So anything that involves that thing right there is called a root. And then if there's an expression, we call either a root expression or a radical expression. Okay? A lot of these words are kind of interchangeable, root and radical. Now there should be a number out front here. Okay, usually it's a 2. And if it's a 2, it's usually not written. Okay? Could be a 3, could be a 4, could be a 5. And that just tells us what root we're taking. Okay? We call that number out front an index. Okay? There is going to be a number on the inside. And that number on the inside is called a radicand, and that's the next vocabulary word I have here. It says it's the number underneath, or sometimes people say it's on the inside of the radical or root symbol. Okay. that index number, it's much like if I were to write y, what is the coefficient in front of y? What is this number out here that we usually don't write? It's 1. What is this exponent right here that we usually don't write? 1, okay? So if I ask you to write y, the variable y, and that's the only algebraic term I want you to write, you usually just write y, but you could write 1 y to the first. Same idea with the root or square root. We can be specific. We can write something like this and be very specific. Square root of, let's just say, 9, which is exactly the same thing as just writing that without having to write that number there. Okay? Those two things, those notations mean the exact same thing. A lot of textbooks don't get into that. A lot of teachers don't get into that. And I think that number up front scares people. Like, well, previously it wasn't being used. Now this question's being used. What does it mean? Okay? And basically what that number out front means is that we are looking for, I'm going to come down here to the square root term. Okay? Square root is a symbol for another number in which you multiply it by itself to obtain a number underneath the radical. Okay? So, this is referred to this red square root of 9. We call that square root of 9. A lot of times people call it radical 9, which is fine. When I say radical 9, I'm talking about square roots. Okay, so those things kind of mesh as well. But this number, I guess that's the index, which basically tells me how do I, an index in like a textbook or maybe some other resource tells you how to find or where to find something, right? Or how to find something. Let's say I go to the index and I'm looking for, let's say I take one of my stats books here and I go back to the index and I look for the word probability. It's going to tell me what page to go find probability on, right? That's what an index does. It tells me how to find something or where to find something, okay? When I tell you that my index is 2, it's basically telling me a way to find this number 9. And the way that we find that number 9 is that we're looking for a number that I multiply by itself this many times 2 to get 9. Does that make sense? So if the index out here was a 3, I'd be looking for the number that I multiply by itself 3 times to get 9. If it was a 4, I'd be looking for the number that I multiply by itself 4 times to get 9. Okay? And when I say number, I'm talking about real numbers. So it's not just like 1, 2, 3, 4, 5, 6, 7. It's not just my integers. It could be any decimal that I could come up with. And a lot of times they end up being irrational numbers. Okay? A prime number. Okay? A prime number by definition is a number greater than 1 that is only divisible by 1 in itself. Okay? Now you could take any two things and divide them, right? Okay? So I could take I could take 5 and divide it by 7, right? But because I have essentially a remainder here of 0.714, okay, we do not say that 5 is divisible by 7. Does that make sense? Okay? If I have 15 divided by 7, I'm doing the division. I can divide any two things I want to, but I would not say that 15 is divisible by 7 because there's a remainder here, right? Does that make sense? Okay. But if I take 35 and divide it by 7, is there a remainder here? No. Okay, so there's no decimal or portion. So here, we would say that 35 is divisible by 7, or 7 does divide 35, because it does it evenly. Does that make sense? Okay. So prime numbers are numbers in which only 1 and that number divide into it evenly. Okay. There's an entire branch of mathematics called number theory that investigates prime numbers. Okay. You guys know? Give me some prime numbers. What's the smallest prime number you guys can think of? Not 1, because by definition, number greater than 1. So 1 cannot be prime. 3 works, but 3 is not the smallest. 2 is the smallest prime number. Anybody know anything unique about 2 as being a prime number?
It's always the simplest.
Okay, so it's broken down as far as it'll go. But well, let's look at a couple other prime. What's the next prime number after 3? 5? Then,
What's the only even prime?
okay, so 2 out of all the prime numbers that exist is the only one that is even. Okay, so just give you a handful of these. So 7, 8's not prime, 9's not prime, 10's not prime, 11, 13, 14, 15, 16, 17, 19, 23, 29, 31. Okay. Now, we got a lot of them early on, but the larger the numbers get, the more sparse prime numbers are. So let's see. We might be able to find a short list of prime numbers. And if you ever question whether something's prime or not, do a quick Google search. Let's see here. But first, 10,000 prime numbers. What's interesting about prime numbers, and this is a study that like people that are interested in prime numbers do, is that we find out that those two are kind of like back to back, right? In regards to being odd, they're back to back odd numbers, 3 and 5. 5 and 7 are back to back. Okay, now 7 and 11 are not back to back, but 11 and 13 are, right? 13 and 17 are not back to back, but 17 and 19 are. 23 and 29 are not, but 29 and 31 are. 41 and 43 are back to back. 59 and 61 are back to back. If I search through here, what we're finding out is that a lot of our prime numbers, once you find one of them, the next prime number, a good probability, the next one is the next odd number. Does that make sense? Okay. Now that's not always the case, but a branch of mathematics is very interested in that. So the argument is, or I guess the investigation that people do, they want to know, how right now we've got out to, 104,729 as being the last prime number. What is the next one? Okay. Well, maybe we would check 104,731 and see if that's the next one, right? Because that's the next odd number. But we have prime numbers, and we have knowledge of prime numbers that are millions of decimal places long. Okay. But between the last prime number that we found and the next prime number, there might be millions of numbers in between them. Does that make sense? Okay. Does anybody know the reason for maybe wanting to know things about prime numbers? Let's take 104,729. 104,729. That's a prime number. No. So let's take 104,729. Okay. Let's say, so that's the prime number. Let's say that we have a bank account number. Yeah. Let's have a bank routing number. Let's say, let's just be, so like bank routing numbers, a lot of times are like 12 to 13, 14 digits long. Okay. So let's just say my banking routing number is 35. Okay. So everything that I do online banking attaches to James Fay with this number 35. Does that make sense? Okay. So when I go to like PayPal, or I go to eBay or Amazon or whatever, pay my car payment, it's going to, that platform that I'm paying on is going to access my bank account using that routing number, right? Okay. And I also have an account number that's attached to it. So this is just a giving you a not an extremely detailed way that this is done, but gives you an overall view of what happens. So if I'm communicating with, if I'm online, okay, and I'm trying to access my stuff, I'm going to submit through Amazon or whatever my information, okay? But what happens is that my banking information gets multiplied by that very, very large prime number. And that turns into $3665515. Okay? That number is what is transferred through the data lines. That's the number that goes through your Wi-Fi into the cables that then take that to Amazon or take that to wherever. Does that kind of make sense? Okay. Now, why would I want that? Because there is someone, usually, out there. So if this is Mr. Fay working on his laptop, okay, there are transmission lines that are going to go to, let's say, Amazon. Okay? But there are going to be bad people in the middle here that are trying to capture the data, the information that is being sent through there. Does that make sense? So somebody's able to extract that information. If it was just 35 coming through there, they extract that information. Now they have my name and they have my bank account number, right? They can do anything they want with that, right? They can drain my bank account. Does that make sense? But now, if that person is still there and they capture my information, what they capture is my name and that number right there. How can they get, so they got my name, but they know that this number is not my bank account. How can from that number can they get my bank account? Not square root, close. What do we do to create that number? We multiplied, right? So how would I undo that? Divide. But the only way that they can divide and get 35 is if they know the prime number that I use to multiply to get that number, right? So what they have is they'll have a computer. So they'll take this number 3665515 and they'll have a computer program that basically takes that and starts dividing it by these prime numbers. Okay? And in my computer, so that's the number I chose. That was the 10,000th. That was the 10,000th prime number. Does that make sense? So their computer program is going to have to run through 10,000 divisions before it gets to my bank account number. Does that make sense? So we'll take that number and divide by all of those. It'll get an output. So once it gets an output, it will then, that computer program or that hacker will say, okay, can I try accessing their information with this number? And then it lets them in or doesn't let them in. If it doesn't let them in, it goes to the next prime number and divides by that. And then they try to log in. Does it let me in? Does not let me in. If it doesn't, they say, well, let's go divide by the next prime number, try to log in. Does that make sense? They're kind of a trial and error type thing. So the computer program, think about this. Computers can calculate things very fast, right? So 10,000 prime numbers for a computer to do the division on that 3551665 number, for computers to do the division using these prime numbers would be very quick. Okay? So what we're interested in is getting those prime numbers to be much, 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 much larger than what they are. We want our prime numbers to have millions of decimal places. Okay? Because then that will bog down those hackers' software and will not allow them to hack into people's information. Does that make sense? You know what that process is called?
Can you repeat yourself?
It's called, you guys ever heard the word encryption?
Yeah.
Okay, like text messages are encrypted, emails are encrypted. That's encryption. That is the process of basically taking a message, encrypting it, which means basically codifying it, making it something else, and then transferring that to a source. And then the source, like Amazon there, Amazon would know
what the prime number was that generated that encrypted message. Does that make sense? So they could unencrypt it. Okay, so they could decipher it and actually read that this is my bank account, that kind of thing. Does that make sense? Okay. So that's maybe a reason why we like prime numbers. Now, people have been investigating prime numbers for hundreds, thousands of years. Okay. Not until recently do we really have that application. Okay. You know, working bank accounts online, that kind of stuff, that's within the last, 25, 30 years. Okay. So, been working with prime numbers, not really having any need for them other than human curiosity until 30, 40 years ago. And now we can start encrypting things and actually have a great use for them. There are projects. Cal Berkeley is one of the main universities that is interested in this. They will offer like contests for like, if you can find the next largest prime number, like it's like $1 million. Okay, they will pay out $1 million for it. Okay, but in order to do that, you have to build a supercomputer that is probably worth a couple $100,000, and then write the software and algorithms and all that kind of stuff that does the division. All right, so that's what prime numbers are. Okay, what's a composite number?
Okay, it's like constant and vowels, right? If you know what a vowel is, you know the antithesis being a constant, right? So A, E, I, O, U are vowels, correct? Sometimes Y. Okay? But everything else then must be a constant, right? So if I know what prime numbers are, numbers that divide themselves, that are only divisible by 1 and 17, then, or not 1, 1 in themselves, 17 is prime. But numbers that divide themselves by 1 in themselves, those are prime. So then every other kind of number is composite. Okay, what's the word composite mean? If you compose a paper, isn't it made up of an introduction, a body, and a conclusion? It's made up of 3 parts, right? You got composite like decking or composite siding on your house. It's made up of multiple materials. Does that make sense? So something that is composite is made up of multiple things. So a composite number is a number that is made up of multiple other numbers, but done through multiplication. Okay? So like the number 8 is composite. This is made up, you can figure it out, find it by multiplying by 2 and 4, right? Okay? One of those numbers, 2 is prime, but 4 is not prime. So that's the added kind of information of the composite number. It says a positive integer that can be formed by multiplying 2 smaller positive integers
In one divisor other than 1 in itself, or it has at least one divisor other than 1 in itself.
Okay? So like, I don't know, 15. Okay? 15 is composite because you go 3 times 5. Those are other numbers other than 1 in themselves, right? Okay? Square root, symbol for another number in which you multiply by itself to obtain the number underneath the root.
Here an example, radical 16. Okay, we can refer to this several different ways. Terminology kind of stinks here, I think, because a lot of people call this root 16, which is fine. Some people call it radical 16, which is also fine. And some people call it square root 16, which is also fine. I like square root 16 because it tells me that I've got a 2 right there. If I just say root 16 or radical 16, I'm telling everybody that there's an understood 2 here, but square root is more informative, I believe. So that's what a square root is. Okay, it's a stat. Radical 16 or square root 16 is a symbol for the number 4. So I take 4 times 4, do I get to 16? Okay. Prime factorization. Prime factorization is the procedure for rewriting every integer as a product of a series of prime numbers. It says every composite number can be written as a product of smaller prime numbers. So no matter what number you give me, okay, we should be able to multiply a set of prime numbers to generate that. Okay? And that is going to allow us to do exactly what we need to do when we want to simplify radicals. Okay? So when dealing with radicals, we want them to be simplified, much like always. We want fractions to be simplified. It says if a radicand is prime, then it's already simplified. So if I ask you what's the square root of 7,
because 7's prime, it's already simplified. If I ask you what's square root of 19, it's already simplified. Okay? Square root of 19, does that make sense? They're saying what's 1/2 simplified? Already 1/2, it's already simplified. So simplifying radicals is simply trying to find the largest perfect square that divides the radicand evenly. Okay? Says we will have several different techniques that allow us to do this. Technique 1, I think, is the longest, but it's the most fail-safe way of doing this. Okay? It's what all our other techniques kind of base themselves off of. First thing you're going to do is, in order to complete this technique, you simply take the radicand and you find two numbers that are going to multiply to generate that value. Okay? So basically we're going to factor the radicand. Okay? Once you do that, you're then going to take those two numbers and find the values that multiply together to get them. So you're going to factor those two values. And you keep doing this over and over and over again. You keep taking numbers and finding their factors. So it's going to create branches of a factor tree, and you keep doing this until the branches terminate at either an integer that is prime or an integer that is a perfect square. Okay? We, right now, are going to do it to where they are prime. So you're going to, all your branches of your factor tree here in a little bit are going to terminate at prime numbers. Okay? You're then going to circle pairs of each prime number. Okay, pair refers to the number 2, right? The amount 2. Okay? Says the circle numbers will be written out in front of the radical symbol, multiplied together if there's more than one. And the numbers that are not circled will go back underneath the radical symbol, multiplied together if there's more than one. And that will effectively simplify your radical. So here we've got some examples. So we're going to take radical 8. Okay? What we're going to do is we're going to take the number 8 and we're going to create a factor tree. So give me two numbers that you know divide 8. 2 and 4. Okay? So that develops branches from 8 in this factor tree. Okay? Now 2, what kind of number is 2? It's prime. So we stop with 2. We're not going to go any further. Okay? And the reason we're going to stop at prime numbers is if it's prime, the only thing that's going to divide it would be 2 and 1, right? And then I got 2 again, and so I could go 2 and 1. And then I got 2 again, I could go 2 and 1. Do you see how this would never let me end if I kept going? Okay, so you stop at prime numbers. Okay, so what about 4 then? 2 and 2. Are they both prime numbers? Yes. Okay. So that's what you do. So what that's basically saying is that 8 can be rewritten as 2 times 2 times 2. It's a product of all those prime numbers at the end of those branches in your factor tree. I take 2 times 2 times 2, do you get 8? Okay, so that's called the prime factorization of 8. Okay. Now, the next procedure said you circle groups or pairs of numbers. Yes? Say again? Not adding or multiplying. So 2 times 2 is 4 times 2 again is 8, right? So, the next step says you're going to circle pairs of numbers. In this case, pairs of 2s. So there's a pair, right? So that, when you circle a pair, one of those comes out in front of your radical. So a lot of times what I like to do is I just write my radical, okay? And then when I circle pairs, one of them comes out in front of the radical, and the thing that is not circled, or the things that are not circled, they go inside the radical. So this 2 right there is that one right there going on the inside. Now what we're really doing here, if you remember what I said at the beginning, is that when we simplify, we're looking for the largest perfect square that divides 8. What is the largest perfect square that divides 8? Perfect squares are numbers like 1, 4, 9, 16. So 4 is the largest number that divides 8, right? By circling these 2, 2 times 2, is that 4?
Okay, so what's the square root of 4? It's that 2 right there. Okay, so that's what we're doing. We're bringing out that largest perfect square. So 2 radical 2 is a simplified version of radical 8. This is what I suggest doing on calculators, because this calculator, now there's a couple out there, there's not a whole lot, that when I type in square root of 8, it will reproduce 2 radical 2. There's not a whole lot, so Jenna has one that does that, okay? So I got radical 8. Now you can't rely solely on that because there's going to be things that we do algebraically that is going to kind of, befuddle those people that rely only on the calculator to do this, okay? So I get radical 8, gives me 2.828, right? If I want to see that I've done this correctly, I should be able to type in 2 radical 2. Does it generate the exact same decimal? Does that make sense to everybody? So because it does generate the exact same decimal, I've got equivalent format. Okay. Let's do one more. Number 12. What are 2 numbers that multiply together to give me 12? 2 and 6. So is 2 prime? So I stop there. What about 6? 2 and 3. 2 is already prime. What about 3? Is 3 prime? Yep. So then I'm going to circle my group of 2's. And one of those comes out in front. Now what goes in underneath the radical then? 3. So 2 radical 3 is a simplified version of radical 12. Okay? Now some people will say, I didn't factor 12 that way. What's another way of factoring 12? Instead of 2 and 6, 3 times 4. So if you went that route, that's okay, because 3 is prime, right? What multiplies then to give me 4? 2 and 2. Is that still 12 is 2 times 2 times 3, right? Is this here still 2 times 2 times 3? 2, 2, and 3, right? So it doesn't matter how you initially divide. Your factor tree might look different than your neighbor's factor tree, depending on your initial choice of factors. However, when you're both done, you should both, in this case, have 2 times 2 times 3. You should have the exact same prime factorization. Okay? Tomorrow, we'll pick up and do the rest of those examples, maybe do some more that are a little bit more complex. But we're going to spend, my vision here is to spend quite a bit of time on these radicals. One, for the mere fact that it's something that I think gets overlooked in Algebra 1 a little bit, okay? But then 2 is something that gets used a lot in your other courses, which we then struggle with because of how it was overlooked in Algebra 1. Okay, so we'll spend quite a bit of time on radicals in the next couple weeks.